everyone, in this video we're going to go through the solutions to this term 2 test. So the solutions are already up, but I'll just talk to them and talk you through them as best as I can. Okay, so for the first one, we've got solve the equation of 3 to the power of 2x minus 3x minus 12 equals 0. Now these are common questions on exams could be in this format, and they're usually easy to recognize. So the more you're exposed to it, the more you will actually start recognizing the method to solve them. So basically you've got your base, whatever it might be, and it's usually a common base there, and to the power of x. Okay, so it could be something like e to the power of 2x plus e to the x. So your base is e, but recognizing, you know, you've got these three terms and basically we're going to turn it into a quadratic. All right, so allowing k to equal the 3 to the power of x, because you can see that's your common term, I guess, in each, it's not, I shouldn't say common term, but you can see your base 3 to the power of x is common to both the first two terms. So then we can rewrite our equation as k squared minus k, and then that constant on the end minus 12. Now we've turned it into a quadratic, which then makes it a lot easier to solve. So we need two numbers that when multiplied give us negative 12 and when add give us negative 1. So not a hard quadratic to solve. So if you've got a monic quadratic, so that just means your coefficient of k squared is 1, then look to factorize it quite simply like this one. If it is one that can't be simply factorized, then you need to use the quadratic formula, which is a bit of a pain in the butt. But yeah, there's no way to do it. If it's a non-monic, you can factorize it as well, but you may have to use the quadratic formula for that as well. All right, so using the null factor law, we get k equals 4 and k equals negative 3. So we do have to then substitute k, 3x for k. So you can see what I've done there. So instead of k equals 4, it's 3 to the power of x equals 4. And then 3 to the power of x equals negative 3. You can't solve for a negative, all right, because there's no solution. So we're only looking at the 3 to the power of x equals 4. So I might just do that over here. So it's 3 to the power of x equals 4. Now if we want to solve for x, basically we take log base 3 of both sides. All right, so that log base 3 of 3, that cancels out and we're just left with 1x, and we've got log base 3 of 4. All right, and that's our final answer. All right, moving along to question number 2. So this one was a bit tricky, but done well, but I think students got stuck because you were, instead of making it simpler for yourself from the beginning, it got a little bit complicated. So you can see what I've done here is we've got the coefficients 4 and 2, and we've got a constant of 2. So just to make it a little bit simpler, I have divided everything by 2. So I've basically taken out 2 as a common factor, and then that means 4 divided by 2 is 2. 2 divided by 2 gives us that 1 there, and then 2 divided by 2 is our 1 there. So it just makes it a little bit easier. When you're using when we're subtracting the same logs, we use our log laws. So we're going to divide. So you got x plus 1 over x plus 5, and this 2 just becomes a power. All right, so we end up with this. Now, if you didn't simplify by taking out that common factor of 2, you probably ended up with x plus 1 to the power of 4 over x plus 5 to the power of 2. And we had log base 2 of that, and then 1. All right, so I'm just going on a little tangent for a sec. Now to get rid of log base 2, we take base 2 of both sides. All right, so we end up with 2 to the power of 1 on this side, which is just, that should already be a 2. So we end up with 2 to the power of 2, which is 4. Now at this point, you could think, oh my gosh, You're never going to be expected to expand this. All right, that is way too time consuming. So you really need to think smart about simplifying it. The good thing is 4 is a perfect square. So if I took the square root of that, and I could take the square root of my numerator and the square root of my denominator, I do end up with x plus 1 squared over x plus 5, which is equal to 2. Okay, so you're getting back to the same point as this. So always think about how can I make it simpler for myself, because if you are expanding this bracket, you should think, okay, I'm not doing it the simplest way and it's designed for me to do it a simpler way. How can I go about that? All right, so let's go back to the question. Okay, so we're going to multiply both sides by x plus 5, which I've done here. And then we're just going to expand this bracket. So I've expanded here to get the 2x plus 10. Because we've got the same term on both sides, they can just cancel out. And then I've subtracted 1 from both sides. So that's how we get x squared equals 9. And then take the square root of both sides. Just remember you get both a plus and a minus. So you get both x equals 3 and x equals negative 3. You do need to test both solutions. So you've just, I might just do this in a different color. So substituting into what I've just highlighted in yellow has to be greater than 0. So substituting into the first bracket, I get 4. Substituting into the second bracket, I get 8. So that's great. That's one solution. Substituting in negative 3 into the first bracket, I get negative 2. And into the next one, I get positive 2. So because for this one here, it's not defined, x can't equals negative 3. So you've only got that one solution. All right. Sorry, I just had to delete stuff because I made an error. So I am going to just put that back in, and I'll just delete what I had. And I'll start again. All right, so just moving on to question number 3. So we've got to sketch this log graph, and we've got to find the asymptote. So with a log graph, you do have a vertical asymptote, and that's found by basically saying, well, with whatever your argument is, has to be greater than 0. So we've got x minus 2 has to be greater than 0, but we can just let it equal 0 to work out what your asymptote is. So we've got an asymptote at x equals 2. So always sketch that. Remember in your question, it says clearly label any axes intercepts with their coordinates, not just the point. So you need to put the coordinates and any asymptotes with their equation. So after you've drawn any graph, just go back and say, yep, I've done that and I've done that. You can see I've done the x-intercept working out there. So we have a x-intercept when y is equal to 0. So we just let our equation equal 0 and then we solve. So we get 5.5. Now with your graph, because we know what a log graph looks like, and we know that we've got a the asymptote there. So basically if we go just below the axis, we know it's going to go very close and then it's going to go through that point. But what is happening above the axis? So if we think about log base 2, we can easily work out that, all right, because that is equal to 1. And we can easily work out log base 2 of 0. Not 0, sorry guys, 1. Whoops, just delete that. Of 1, which is 0. And that can help guide us with some points. So with our equation, I might just write this in a different color. It's going to let me choose a color. All right, let's do it here. So our equation is log base 2 of x minus 2 plus 1. So inside this bracket, what do I need to let x equal to make it equal 2? Okay, so I'm going to let x equal 4. So when I put in the 4, so when x is equal to 4, we get y is equal to this plus 1. All right, so 4 minus 2 is 2, which gives us 1, so 1 plus 1. So we're going to have the point 4, 2. So I'm going to put that on my graph. So 4, 2, which is up here. All right, and the other one, oh, I'm running out of room. Let's just do it down to the side here. So we're going to have log base 2 of x minus 2 plus 1. So what would I put in for x to make this whole thing 1? So it's going to be 3. So when x is equal to 3, we get 0. So 0 plus 1 is 1. So our other point is going to be here. So when you're sketching, we just got to make sure we're going to go through those 2 points. All right, and at least it shows you've got some understanding of the direction of your log graph. All right, so moving along. So question number 4, find the inverse of that exponential equation and state the domain and range of the inverse function. So this was done quite well. So when you're finding the inverse, you're just switching x and y, and just take your time. So when we first of all switch x and y, we're going to get rid of this constant first, so that comes over as plus 5, and then I also did this in one step, so that's 4 times e, so we divide by 4. So my left hand side, I'm left with x plus 5 over 4 equals e to the power of y over 2. Now to get rid of this e, we just take log base e of both sides. So you can see I've done that, and then just to get rid of this 2, we multiply both sides by 2. So we end up with this function. Now remember, if we're finding the inverse, we need to use the inverse notation. So you could just at the end of this say, which is equal to f of negative 1 of x, and done. Smiley face, all good. I've just rewritten it because I just felt it was a little bit neater. Now for your domain and range, so remember your domain and range switch. So if we did the domain of this graph, all right, so it's an exponential graph. It's going to be any real value. X can be anything. Right, it can be negative, it can be positive, it can be 0. But your domain, your range, and remember with an exponential graph, you do have a horizontal asymptote, and this one has been shifted down 5. So we're going from negative 5 to infinity. So that's why, and then your domain and range switch for your inverse. You could have also just looked at this and got your domain from that, and also realized that your range could be any real value if you had an understanding of a log graph. And there's your log graph there. So you can see the y values aren't restricted. All right, question number 5. So this was done really well. So the range of a sine or a cosine graph is usually negative 1 to 1. So just think about the transformations that are happening to your y coordinate. So we've got the 3 changes your dilation, it's your dilation factor, and it's also your amplitude. So basically you're multiplying that by 3, and then it's been shifted down 2, so we're minus 2. So just following those transformations, so negative 1 times 3 minus 2 gives you negative 5. 1 times 3 minus 2 gives you 1. And just make sure you have your smaller number first. All right, can't go second, it's got to go first. Now your period, our value of n is the coefficient here. So pi on 4, pi x on 4 is the same as pi on 4x, so that's your value of n. So remember your period is just 2 pi on n, and that's the same as 2 pi divided by n. So writing it that way is sometimes easier, but that was done quite well to get 8. All right, question number 6. So here we're solving for 2 sine x on 2 plus 1. So just letting it equal 0, probably should have had that in the question. All right, so we get inverse sine of a half. All right, so that negative just tells us this negative here just tells us which quadrants we're in. So we're in, because sine is negative, in the 3rd and the 4th quadrant, but our reference angle is pi on 6. All right, so we're using that reference angle. Remember we solve, I'm just going to change color, we solve for x on 2. All right, so that's what, where is it? We're solving for x on 2. So you can change your domain, which can make it a bit easier to understand how many times to go around the unit circle, because I saw a lot of people find solutions that weren't within the domain. So if you have something other than just x here, just having a temporary domain does help with how many times you go around your unit circle. All right, so we're starting at negative pi, which is over here. So our first solution is going to be negative pi plus pi on 6, which is in the third quadrant. And then for the second one, we're going to have 0 minus pi on 6. Then we're going around and then we stop. So because we're stopping at pi. Because remember, I did my temporary domain is from negative pi to pi. So just simplifying them, I get negative 5 pi on 6 and negative pi on 6. Now this is where some people went wrong. So we've got x divided by 2. We want to get rid of this 2. So the opposite of dividing by 2 is multiplying by 2. So when I multiply this by 2 and multiply this by 2, I'm basically not going to have the 6 on the bottom. It becomes a 3 because 2 on 6 is the same as 1/3. All right, so just be careful with that. I did see some 12s. All right, question 7. So looking at a general solution, it doesn't explicitly say the general solution, but we're solving for any real value of x. So I'm going to show you 2 ways to do this. So first of all, we're getting our reference angle, which is pi on 3, and it's positive, so cos is positive in the first and the fourth quadrant. All right, so I've ticked them. So that means we're going from, it's going to be too big, from even pies. So even pies are 2n pi, or if you use k, that's fine, 2k pi. So when I'm writing my solutions, and I know I've got it written there, but we are solving for 2x. All right, so just so remember whatever is inside your bracket there, that's what we're solving for. We're solving for 2x. And we're going from 2n pi plus pi on 6. All right, that's 1. And then in the fourth quadrant, we have 2x is equal to 2n pi minus pi on 6. Now, I do have to solve for x, so we're going to divide everything by 2. And remember, dividing by 2 is the same as multiplying by a half, so if you want to do that. All right, and that's how we end up with the, hold on, why did I write 6 over there? Sorry, guys. Silly me. I was looking at the wrong thing, I think. All right, so that should be 3. All right, so to get, so 2x divided by 2 gives us our x. This 2n pi over 2 gives us n pi, and then pi on 3 times a half gives us our pi on 6. Now you need to have this where n is an element of z, so n is an integer. If you don't have that, you're not going to get full marks. All right, you'll only get 1 mark. All right, I feel like there's a lot of highlighting going on, so I might just unhighlight this. Now another way you can do it, I'm going to get rid of this as well, so if you wanted it, you can rewind. All right, so the other way you can do it is to find your 2 solutions. So we're solving for 2x. So your first solution is just pi on 3. And your second solution is 2 pi minus pi on 3, which is 5 pi on 3. All right, so then we are going, sorry, let's just get rid of that 2. So we're going to divide by 2 or times it by a half, which is the same thing. All right, so we get x is equal to pi on 6, and this one is x is equal to 5 pi on 6. So remember, you're just going around each time by your period. So our period for this one is 2 pi on n, where n is 2. So your period is pi. So basically you're going to be adding multiples of pi each time. So plus, let's do k for fun, plus k pi. All right, and you don't have to do minus, all right, because the k value can be minus anyway. But we do have to put where k is an element of z. You don't have to do it twice because there's your 2 solutions. All right, so some of you did do it that second way, and some of you did it the first way. Both are fine. And yeah, both are correct. So it's up to you what you find easier to do, basically. And yeah, they are the same thing. All right, question 8, moving on to the tan graph. All right, so with the tan graph, so I've got a tan graph and we're going from 0 to 2 pi. We have to label asymptotes and any intercepts with their coordinates and the coordinates of the endpoint. So 3 things to do, and also make sure that we're drawing the tan graph correctly. So let's have a look at the asymptotes first of all. So I might just do that down here. Now, with a normal tan graph, so tan x, you're going to have asymptotes wherever cos x equals 0. That's because tan is equal to sine over cos. And we can't divide by 0. We can't divide by this. So that's why we have our asymptotes. So if you think of your unit circle, wish I didn't have that so big, but it's all good. Cos is going to be equal to 0 here and here. So it's 0 at pi on 2 and 3 pi on 2. And then multiples of them, obviously. So when we've shifted this graph by pi on 4, all right, so this x plus pi on 4, let me just do it in a different color. Yellow. All right, so we've shifted it to the left pi on 4. So my asymptotes, which were at, just write a different color. So my asymptotes were at pi on 2 and 3 pi on 2. I've now had that shift to the left by pi on 4. So we're going to go minus pi on 4, minus pi on 4. So that gives me pi on 2 minus pi on 4. If you wanted to, you could change the denominators. So pi on 2 is the same as 2 pi on 4. So I get pi on 4. Then 3 pi on 2 is the same as 6 pi on 4. Sorry, is that a bit of a brain fart? 5 pi on 4. So you can see I've put those two asymptotes in. X equals pi on 4 and x equals 5 pi on 4. Now I haven't had a vertical shift. A vertical shift with the tan graph just makes things such a headache. And there hasn't been any vertical shifts, so it's awesome. So that means my x-intercept is just going to be halfway between my asymptotes. So you can kind of see the symmetrical nature of this. And so halfway between pi on 4 and 5 pi on 4 is 3 pi on 4, which is here. All right, you can see that. And then I just drew my tan graph in the middle. Now we did have to have it either end as well. So we've got this end point here because we're only going from 0 to 2 pi. All right, so my endpoints are at x equals 0. How come I was wondering where that pi on 4 came from. So substituting in 0 here. So 0 plus pi on 4 and then 2 pi plus pi on 4. So just getting these values, knowing your exact values, and pi on 4 tan pi on 4 is easy to remember because sine and cos are both the same there. So when your numerator and your denominator are the same. So that's why our endpoints are 0, 1 and 2 pi 1. So just making sure you've got your endpoints. So I think for that sort of question, the hardest part would actually be those endpoints. All right, and making sure you finish at 2 pi because you're not ending on an asymptote, if that makes sense. So, and you've got to clearly mark in that point. All right, moving on to, now I don't know why, well, I do know why question 10 comes before question 9 because we did have it around the other way because we thought question 10 was easier than question 9, which is very true. All right, so it tells us it's a cos graph. All right, so looking at that, it's been reflected. It hasn't had a horizontal translation, so which it could have, and it would might not need a reflection, but there's no reflection happening here. We only have to find the value of A and B. All right, no, excuse me. So I know that A has to be negative. So A isn't your amplitude necessarily, it's just your coefficient of cos. You do work out your amplitude to get A, but A is also negative, even though your amplitude's not negative. All right, your amplitude, we haven't had a translation, so it's just a distance from this halfway point, which is here. So we're going up 2 and down 2, so that's where the 2 comes from. So A is equal to -2. And then for one period, let me just sketch that. So think about going around your unit circle. So we're going, there's your first quadrant, there's your second quadrant, there's your third quadrant, there's your fourth quadrant. So your period is pi on 2. So that's what I've written here. So basically you're solving for, oh gosh, that was a bit too dark. You're solving for B. All right, so 2 pi on n, in this case n is B, you're just solving for B. Now if that was too hard to see you on your graph, what I've done in purple, you can also just go, I'm wondering what's an easier, oh, they're all pretty much the same, aren't they? If we had a better scale it might be easier to see, but with a cos, I was going to say you could go, whoops, it's hard to see. You could go like that, but because of the scale it's a bit hard to see that. All right, so you did have to find A and B and the rule for the graph. Okay, so if you found just A and B, you don't get you don't get 3 marks. You'd probably only get 2 marks. So just substituting them back in, then you get your full 3 marks. All right, question 9, or the last question, is very hard because having an understanding of what's happening with your cos graph will help you find B. All right, so that's the trick with this question here. This A is between 0 and pi is because you could have infinite values for A, so it did have to be restricted, so you just got one answer. If it was not restricted, you would have to then have your answer in a generic form. So it's better if it's restricted. Now, if we look at our equation, so we've got cos x minus A plus B. So our amplitude is 1. All right, so that coefficient of cos is 1. So that means with my cos graph, if you think of your range, it would go from -1 to 1. But our graph has been shifted up. Oh, didn't mean to do that. I want to highlight it. It's been, oh, come on. It's been shifted up by B. Now, when you think about it, we've got this 3 and this 1. All right, so that helps us work out. So this is going to be 1 and 3. So that's our new range. And the reason I know that that's our minimum and our maximum point is because you want your distance between these to be 2, right? And this is also 2. So it can't be anything other than, just being shifted up, and your minimum and your maximum. This 2, sorry, I was just getting distracted, is this 2 is not the same as your value of B. All right, it's just telling me that it hasn't been shifted up by more or had a different amplitude. All right, so if we're going from a range of -1 to 1 to 1, 3, basically all I've done is added 2. All right, there's been no dilation factor because our amplitude is 1. So it's only been shifted up by 2. So that's how we get a B value. A B value of 2. Oh, my pen's not working. B equals 2. Now, knowing that, I can now substitute that into my function, and it makes it so much easier to answer for A. So once you've found B, it just makes A a whole lot easier. So you can use either this first function, this one here, or equation, or you could use this second equation. It doesn't actually matter. I just use the first one but you'll get the same answer for both. So f of pi on 2 equals cos of pi on 2 minus a plus 2. So I've now put in my value of b there, and it's equal to 3 because that's what it says in the question. Then I've just subtracted 2 from both sides. So take away 2, take away 2. So I get 1. And then to get rid of the cos, we do inverse cos of 1. So thinking of your unit circle, cos is 1 here at 0. So inverse cos of 1 is 0, and then we're just solving for a. So a is equal to pi on 2. Okay. If it was a generic solution, you can see cos would be equal to 1 every time we go around the unit circle. So we would have let me just think. So this would be 2n pi. So you would have a is equal to 2n pi plus pi on 2, where n is an element of z. So that's if you had to have a generic solution. But for this one, because your domain, your restrictions on a were from 0 to pi, we only have that one solution. All right, and that's it. Good stuff, guys. Very hard test, but hopefully with more practice, you'll build your confidence and yeah, everything will be well.